Okay, so for your post-lab calculations, I'm just going to do a couple of these, and I'll show you how to do the first part. So like for this question, the 5 mil, and then the process will be same for the 20 mil. You just have to change a couple of things. So the first thing that you want to recognize is that you're dealing with HCl. So we have 25.0 mils of HCl, and 5 mils, I'll say 0.0 mils of NaOH. This is 0.100 molar. All right, so they have the same molarities. One thing that you want to, again, recognize after you've written down your beginning information here is that this is a strong acid, and we have a strong base. All right, so if you have a strong base and a strong acid, these are at the end point or the equivalence point going to neutralize each other out, but we just have to figure out how to set up this equation. So one thing that you can do, and I'm not sure if this is how it's done in your lecture, but this is how it made sense to me when I was figuring these out, is to make the Rice table. Okay, so again, because we're dealing with strong acid, strong base, we are dealing with OH minus plus H plus, which is the acid, and that is going to give us water. Right, and then when you're filling in these tables, again, I'm not sure what extent you've done this in class, these have to have mole amounts. So we need to determine the moles of base initially and the moles of acid initially, and then the moles of water will be 0. So I'm just going to put 0 here for that one. So to get moles of acid, so we'll come back to this Rice table, but I'm going to fill in here how we do the moles of acid. So to get moles of acid, we're going to multiply the volume in liters. So this would be 0.025 liters times the molarity, 0 moles per liter, and that should get you 0.0025 moles of HCl. All right, and then we want to do the same thing with base. So I have moles of base, 0.005 liters times 0.100 moles per liter. That should be 0.0002 moles. Sorry, that should be 0.005. Okay, so now we have our mole amounts that we need to fill in our table. So for base, I'm going to put in 0.003 2 zeros. I'm sorry, 3 zeros. 3 zeros and a 5. And for acid, 0.0025 is the initial, and our initial for water is 0. The change now, all of the OH that is being added is going to get used up by the strong acid. So we're going to subtract 0.0005, and then this will be minus 0.0005. And then the water will be plus 0.0005, which at this point doesn't matter in the equation. Sorry, this pen is awful here. Okay, so our change then is 0. This is 0.002 moles, and then we have the water here. So if you remember, pH equals the negative log of H plus. Here we have the moles of H plus. So H plus equals moles. This has to be in concentration, or moles per liter. So we have the number of moles. So I'm just going to put here equals 0.002 moles. And the liters, our volume, is the total volume that was added. So we had 25 mils plus 5 mils. So this is 0.030 liters. So we're going to divide that. The concentration here is, this concentration is 0.067 moles per liter. So now we can plug this back into that equation. So pH equals the negative log of 0.067, and that then should equal 1.24 when you take the negative log of that. So that's how you would do the first part of this calculation with 5 mils of 0.1 molar sodium hydroxide. For the 20 mils, the process is the same, except your starting moles is going to be 20 mils times 0.1 molar, so you'll have 0.002 here. Otherwise, the rest of the process is the same. So that's how it is for the first one. So I'll let you guys do the second one. Number 2 is a little bit different. So we have 25 mils of 0.05 molar ammonia. So ammonia is a weak base. And HCl we know is a strong acid. So this titration, or I'm sorry, this calculation is going to be a little bit different because we have to use the Henderson-Hasselbalch equation to get to the pH. We can't just depend on the concentration of acid because we also have the weak base in there playing a role in that. But we can still use the Rice table. So the reaction here is going to be H plus, and then we're going to add NH3, and that's going to give us ammonia, or NH4, ammonium, NH4 plus. So our initial, again, we're going to find the moles of acid and the moles of base. So I'm just going to do moles of acid first. So to get moles of acid, we have 0.005 liters, again, times 0.10 moles per liter. So our moles, again, this needs to be in moles. So this ends up being 0.0005. And then for moles of base, we have 0.025 liters times 0.0500 moles per liter. And that will be 0.00125 moles of NH3. This is moles HCl. Okay, so we can fill it into our table. So for H plus, we have 0.0005, and H3 is 0.00125. And those are, again, in mole amounts, and that's not in moles per liter. Okay, so then, and also the ammonium at that point is going to be 0. All of the H plus is going to get used up, so that's going to be minus 0.0005. And this will be plus 0.0005. All right, so our equilibrium here is 0. Okay, so do your subtraction. We have 0.00075 and then 0.0005 for that. So again, we need to put them into molar amounts. So we need concentration in moles per liter. And then again, you're just going to do that by taking the moles divided by the total volume. So mole divided by total volume. So for the NH3, NH3 equals the 0.00075 moles over the total volume, which is in this case again 0.03 liters. So this comes out being 0.025 moles per liter. And then for ammonium, this is 0.0005 moles, 0.03 liters. So this is 0.0167 moles per liter. Okay, so we have our NH4 plus and NH3 plus, and because this is strong acid and weak base, we need to account for both of these things. We can't just take the H plus concentration, especially since this H plus is all used up. So we have to use the Henderson-Hasselbalch equation. So Henderson which is the pH equals pKa plus the log of base over acid. And that's again in moles per liter, which we already have. If we look back at the word problem here, we're given the Kb, not the Ka, and which is what we need here. So to get to Ka, you have to remember that pKa plus pKb equals 14. And we can get the pKb by taking the negative log of the Kb. So I'm going to do pKa, this is just kind of on the side here, pKa plus the negative log of 1.8 times 10 to the negative fifth equals 14. So again, this is pKb is equivalent to taking the negative log of the Kb, which was given there. So we have pKa equals negative log of this. So after you do the math, pKa equals 9.26. So now I can plug this into my equation. So pH equals 9.26 plus the log of my acid here, which is NH4 plus. Zero, 1, 6, 7. Oops, sorry, base. I have it written here. So it is base over acid. So our base is 0.025 and the acid is 0.0167. And then once you do the math for that, this comes out to the pH equaling 8.44. So again, you would do the second half of the equation the same way, except now you're going to switch the 5 mils here to 10 mils. In this last problem, we have acetic acid and sodium hydroxide. Sodium hydroxide is our strong base, and acetic acid is a weak acid. So we're just going to do the same rice table. So our strong base is OH minus. This is our weak acid, and it forms acetate plus water. And again, to get the initial moles of acid, I'm just going to do what we did before. Okay, so I've done the calculations here just to save some time, but the moles of acid process is the same, 0.025 liters times the concentration, and then 0.005. So just fill in your table. Okay, so we end up, sorry about that, we end up with 0 here, this is 0.002, and this is 0.0005. So again, we're going to use the Henderson-Hasselbalch, and so we need to get the molar amounts. So we need concentration in moles per liter. So I'm going to go ahead and just pause here and do that while you guys work on that. Okay, so your acetic acid concentration is the 0.002 moles over the 0.03 liters, and then for your acetate is 0.0005 over the 0.03. So again, the 0.03 came from the total volume here. So when you do your 20 mil calculation, it's going to be 45 mils that you're dividing it by, or 0.045 liters. So now we have the concentrations for the acid and the base, then we can plug it into Henderson-Hasselbalch. Which is base over acid. So the pKa we are given is, is the Ka, but that's the negative log of 1.8 times 10 to the negative 5th, plus the log of base over acid, and then when you do that calculation, you should get 4.13. Okay, so hopefully that helped with the calculations. Really the big thing is recognizing if it's a weak acid, strong base, weak acid, weak base, strong acid, strong base, putting it into the rice tables so that you can figure out how much of what is where, getting it into the concentration, and then using the HH equation there.